Okay.
Good afternoon, everyone, and welcome to today's presentation by Dr. Alexandros. Dr. Emboras is currently a lecturer in the Department of Information Technology and Electrical Engineering at ETH Zurich. And since January 2018, he has coordinated the Center of Single Atom Electronics and Photonics at ETH Zurich. Following his PhD in electrical engineering in 2012, he worked at the Hebrew University of Jerusalem. And from 2014 to 2018, he worked as a research scientist where he led at ETH Zurich, where he led the atomic scale research activities at the Institute of Electromagnetic Field. Dr. Emboras, thank you for accepting our invitation to speak in today's seminar, and the floor is now yours.
Well, thank you for the organizer for this kind invitation and also for this kind introduction. For me also, it is indeed an honor to be a part of this amazing online seminar, and I hope that my research will give also ideas and contribute and give you some new information that probably will add some value to your webinar, let's say. Just give me a second now to share my screen. Okay. Yes. So now, given the broad, basically, spectrum, I would say, of audience, I decided to give, to some extent, a rather high-level overview of the field of the hardware-based neuromorphic computing. And before start, I should also clarify that I'm working really on hardware level. So my experience in simulations and modeling is quite limited. And in this seminar, I will talk about opto-electronic memristors, a platform for efficient neuromorphic computing application. Where I come from, basically I come from, I have a tenure position as a lecturer at ETH Zurich, which is located in this, in the city of Zurich, in the one side of the hill. Here we have our labs and our offices, and in the other side of the hill, we have our joint nanotechnology center between IBM and ETH Zurich. This is basically really a nanotechnology center that combines passive and active measures to eliminate any disturbances relevant to nanotechnology, and because of that, we are able to fabricate devices with nanometer precision very reliably. So currently I'm coordinating also the Center for Single Atom Electronics and Photonics, and this is a 12 million research project recently funded by Siemens Foundation. And it started on January 2018, and it's gonna last basically forever. And in this center, we're gonna investigate new class of optoelectronic devices and circuits where atoms rather than electrons are used for the operation principle, and for that I would like to make a functional shift and to move towards neuromorphic applications. This is the outline of this presentation. First, I will motivate why we need to move towards neuromorphic computing. And I will present the case of optoelectronic solution as an efficient platform for neuromorphic computing application. And I will move and describe a hardware element, the so-called memristor, which is the basic element for the neuromorphic hardware. And in part 3 of this presentation, I will present our own toolbox for optoelectronic neuromorphic computing. And I will present their 3 devices. I will extensively describe the first one, memristive electronic switch. And there I will show also an application in deep neural networks. I will describe a memristive photodetector and a memristive modulator, and I close this presentation by giving a conclusion. Good. So let's start with motivation for neuromorphic computing. And it is well known that we are living in a society that is driven basically by data, and this can be demonstrated by providing some numbers. For example, we're using several exabytes of data every day, and the 90% of those data has been created in the last 2 years. And on top of that, we have the Internet of Things revolution, which is forecasting 30 billion of internet connected devices by 2020. And this will generate basically 44 trillion of gigabytes. And on top of that, we have, it is projected that by 2025, we're gonna produce something like 180 trillion of gigabytes. And with these numbers, I would like to say that we need efficient computing systems for data processing in order to be energy efficient. Otherwise, we will not be able to process it. What is the computing challenge for data processing? And this basically can be understood by looking in a real time, in a real experiment. There's the so-called job artist game, where it is an answer and question game. And in this game, the IBM Watson, a supercomputer from IBM, wins against two of the job artist's greatest champions. And again, this was really a remarkable achievement, because for the first time, a supercomputer is winning the human brain. But in order for this to happen, they use 2,800 processor threads, several tens of 16 terabyte of RAM, 80 kilowatt of power consumption, and 20 tons of air conditioned cooling, whereas the brain with less than 2 kilos and probably one of the most integrated machine in the Earth consumes only 20 watts. So again, the human brain consumes only 20 watts. The supercomputer from IBM is consuming 80 kilowatt. And this is, at least in my opinion, really very remarkable. And where does this inefficiency from supercomputer comes from? And this is basically, it comes from the current architecture of the supercomputer, where the memory and the processing unit are physically separated. So, and this means that if we would like to process the f of a, we need to transfer the data from the memory into the arithmetic logic unit to perform the operation and bring it back and save it into the memory. And this back and forth movement of data is what is causing basically the high energy consumption. So now how we can basically solve this problem, and there are basically two ways. One way is to really make advances. We keep the architecture the same, and we make advances in individual elements within the architecture or small modification within the architecture. For example, if we improve the access time of this memory, we can improve the overall performance of the device. And this means that we can access data faster. So we're gonna improve a little bit the system, but this will not be the ultimate solution. And another solution is to bring the memory closer to the processing unit. With that, we can eliminate the distance of traveling the information back and forth. Again, we can have improvements in this system, but this will not give the ultimate solution. And another solution, another way is to make advances in non-von Neumann computing architecture and the so-called neuromorphic architecture. And this neuromorphic architecture is basically inspired by the brain, where the memory and the processing units are collocated. So the F of A now operation is performed exactly at the same physical location as data storage. So the ALU now is not within the processing unit, but it is within the memory. This is why we call it here computational memory. So we don't need to transfer information back and forth between these two, between the memory and the processing. So the computation is happening much more efficient. And what you can see here, it is an electrical neuromorphic computing neurosynaptic array, basically, that is used for neuromorphic computing. And it is organized in a dense, basically crossbar configuration of neurons and synapse. And if we zoom in here, here you can see the zoom, you can see the wires that are crossing each other, and each cross bar point here can store and compute exactly at this, and process information at the same place. And how we do that? We do that by using memristors. I will not give you more details for the moment because I will have a special section describing memristors. But in a sense, it is very briefly, it is a two-terminal device. Memristor, it is shown here, is a two-terminal device, consists of a metal, insulator metal, with a tunable non-volatile resistance. And just I'm telling you from now that this memristor is able to emulate synapses, the biological processes that are happening within a synapse or in a neuron. So what is the problem with this electronic, let's say, neurosynaptic arrays? The problem comes when we try to scale it up. And if, for example, we'd like to put several neurosynaptic arrays within the same chip, we need intra-chip routing of information, which is basically nowadays is happening through dense copper interconnects. And the speed is limited to 1 gigabit per second, and the power consumption is roughly 100 femtojoule per bit. And what basically we need is really 1 femtojoule per bit, and also higher speeds. And at that point is rising the interest for integrated photonics with neurosynaptic arrays. So we think that if we integrate photonic routing, we're gonna benefit, and we're gonna increase the power we're gonna increase the speed and reduce the power consumption. And nowadays there is also some work on all optical neuromorphic computing. And here what you can see, it is an example. Here you can see a waveguide, and here you can see a ring resonator. They use, and here what you can see, it's a memristor. And they use this ring resonator in order to enhance the light matter interaction between with the memristor. And then they end up with a single device which is really large, and although they can perform high bandwidth and low power consumption, this solution is generally bulky compared to electronics, and this is a general problem with photonics. And what we propose here, and what I would like to talk about, it is the electro-optical solution for neuromorphic computing. And in this electro-optical solution, what we would like to take an advantage is the high density feature given by electronics, and the high bandwidth feature given by the photonics. And at the end, we would like to show that this solution is able to really bring the power consumption during neuromorphic operation really low. Here, what you can see, it is a potential solution of the platform that I suggest, and me and my group is working on. And this platform basically consists of electronic neurosynaptic cores. You can see for an example here of 2 neurosynaptic cores, 1 and 2, that in this level, the data are produced electrically. And we have, on top of that, we have the photonic routing. So it is a layer of with different photonic components. And what we can do is to transfer the information from one point to another point very efficiently. The nice thing with this photonic link that we're proposing is all based on memristors, which means all has some memory effect. And what we can do also in the photonic part, we can do also for the first time computation. Normally, we use photonics to make only routing. Here, the idea is to do routing plus computation, and this can be achieved because those components here are all based on memristors, which requires to have some memory effect. So, yeah, so in our group, we already developed some devices. We developed nanoscale memristors for producing the data. We develop memristic modulators to convert the electrical data into the optical one. And we develop memristic photodetector to convert the optical data back to electrical one and then communicate with this neurosynaptic code 2, for example. And all these are summarized in these several papers that you see here. So now, what is memristor? I already said that several times, but I didn't describe in details what is memristor. And this is the second part of my work to tell you what is memristor and why is suggested as the key element for this, as the key hardware element for neuromorphic platform. So I will skip the summary here, and I will move to the part 2, which is the, as I said, memristor as a basic element for neuromorphic hardware. So what is memristor? Memristor is a resistor. It's just a simple resistor with memory characteristic. And the important thing in memristors is that instead of tuning the electronic properties by gating, we tune them by relocating atoms. So normally, all mainly the devices that we have or we use in CMOS environment, we tune basically the electronic properties at the end of the day. Here, we tune, we relocate atoms, and this is how we modify the electronic properties of the whole system. And there are different categories of memristors. The first one, and I will present briefly 3 categories. One is the conductive bridging memristor, where it is shown in this figure here. And basically it consists of 2 metal electrodes, the top electrode, the bottom electrode, and in between we have an insulator. And under the application of a voltage between these 2 electrodes here, we can move atoms back and forth between these 2 electrodes. And this is how we change the resistivity of the resistance of this device. There is another category, the valence change memory, where we move basically oxygen atoms under the application of a voltage or a field. And this is how, again, we change the resistance of this device. So by moving oxygen ions back and forth, we are able to control the resistance of this device. And there is the last category, which is the phase change. And in this category, basically, under the application of an external signal, we can create different atomic ordering. And this different atomic ordering induce some different resistance. And this is what we read at the end of the day. So in this presentation, I will focus only on this conductive bridging memory, and for that, I would like to give you a little bit more details. And to understand the operation principle of such kind of memristors, here I present you a typical current voltage characteristic. The cycle starts with small negative voltages. The device is the one that is shown in this inset here. And under the application of, under increasing the applied voltage, we have ions that are diffused into this insulating material here. And when we reach a threshold voltage that we call it set voltage, we have an abrupt jump in the current, which indicates that the platinum and silver electrodes are connected with some silver nanofilament. And when we reduce the voltage for small negative voltages, we can erase, basically, we can destroy this filament, and the current that is now passing through the device is very low. So what we can do, basically, we can switch reversibly between a low resistance state, the B1 here, and high resistance state, the C here. So we can reversibly switch these two states back and forth through voltage-induced filament formation and dissolution. And the justification that is what is modulated, basically, it's silver nanofilament is coming with an in situ transmission electron microscopy observation, where under the application of the voltage, we constantly look on this junction and we see that there is a filament that is completed, and this is what is basically connected to electrodes, and this is the short circuiting the device. And also what we can see is some partially formed filaments. So the picture that I have in my mind, at least, is what we modulate is between partially formed filaments and completed filaments. And this is how we switch on off the device. So this device is really rich of different physical processes and dynamics. We have oxidation reduction that is taking place. We have ion atom transport, and we have electronic transport. And it is an interplay of different physical phenomena. Really beautiful physics, I would say. And as I said, in this specific example that I'm showing here, we use two resistance states to do binary non-volatile operation 0 and 1. But the nice thing with memristors, we can use it not only as a binary element, but we can use it also as an analog device. So, and here what you can see, it's a programming signal as a function of the time, and below it's the device state, or differently, the resistance of the device as a function of the time. And what I can tell you is that if you choose correctly these programming pulses here, you can induce intermediate states of this filament geometry, and this can be translated basically to different conductance states. So what I would like to say, we don't have only binary storage, but also multi-bit storage in a single device. And what we have, it is essentially an analog storage device, as happening also in the synapse. And this is really an important property when we are trying to train a deep neural network, let's say. The second nice thing for memristors is that they feature the property of integrate and fire, which is exactly the property that, and in that way we can emulate basically neurons. And again, here you can see the programming signal as a function of the time and the device state as a function of the time. And again, if we correctly choose this programming signal here, we can basically modify the state of the device, but when we reach a threshold, which is roughly here, we can switch the device on, and these abrupt changes in the device state is equal to the firing capabilities of a neuron. So to sum up, the programming signal can induce intermediate atomic rearrangement, and the device state is dramatically changed when we reach a threshold, emulate the generation of a spike. And there are applications that demonstrations nowadays that they're using exactly this behavior to train and spiking neural networks. So a quick summary of memristors and why it's really important for as a hardware in neuromorphic computing. With memristors, basically we can implement synaptic or neural behaviors by regulating the state. For example, the resistance or optical transmittance of the memristor. And memristors exhibit non-volatile and analog operation is likely, we can say that we can emulate the synaptic behavior. Memristors exhibit integrated fire functionality, are similar to the behavior that is happening to neurons. Good, and now I would like to go to the part 3, which is our own toolbox for opto-electronic neuromorphic computing. And as I said, I will spend some time on 3 components: electronic switch, memristive photodetector, and the memristive modulator. And let's start with the atomic scale memristive electronic switch. So, as I said also at the beginning, it's, or as I show in this figure before, here what we have is basically the fabrication of several nanofilaments during the application of a voltage. So, and this is a big challenge because the filament formation is really a stochastic process, which could be a key limiting factor of reliability and repeatability. And if it is a limiting factor in the hardware level, will be also a key limiting factor also in the software level. So differently, if we don't know exactly at which state we are, I think we cannot also simulate the behavior, so we cannot efficiently train also an algorithm. So for that, since this is a key limiting factor, we design an electronic switch based on an ultra-sharp 3D tip technology. And based on this 3D tip technology, we were able to achieve performance improvement, in particular, reliable and low power consumption and fast operation. Excuse me. So how does it look like? The device basically consists of silver, silicon dioxide, and platinum. And one of the 2 electrodes, in our case here, silver, it has a tip-like configuration. And under the application of the voltage, we diffuse silver ions into the matrix, into the silicon dioxide, and we create these basically nanofilaments. And the voltage-induced reversible formation and dissolution of this nanofilament can create the states, the non-volatile states that we need. The key thing in this device is that this sharp tip here improves the field confinement and promotes the formation of a single nanofilament, which I will show you that induce also better reliability. And the motivation of the tip-like configuration can be understood by this very simple calculation of the field. And what you can see, if we have a field like this case here, the tip-like configuration induces better field confinement. And this better field confinement compared to the planar structure, which is here, can lower the switching volume. So we can concentrate to the formation of really a single nanofilament. We have better control of filament growth. And what we see experimentally, we see higher speed and lower switching voltage compared to the state of the art. I will not give details in this presentation about how we make that. I think it's out of scope. Briefly, we use an AFM heatable tip to transfer the AFM tip into the silicon, and how the device looks like. It looks like that. On the bottom, we have the platinum electrode. On the top, we have the silver electrode. And here, what you can see, it is the tip configuration. And we demonstrate that there is a tip there by performing an AFM image. And here you can see how it looks like. And also, we cut this device in a cross section, and we see also that there is indeed a tip with a radius of 10 nanometers, which is something really remarkable compared to the state of the art. And we prove also that our technology is scalable. And here you can see an array of 2x2 of 2x4. Remember that we're working on a research level. We're not making huge arrays, crossbar arrays. The remarkable thing is that we have a minimum pitch of 30 nanometer, and we reach intensity of roughly 10 to 8 memristor per millimeter square, which is something comparable also to the state of the art, what the industry basically can do. And to see that the tip and the non-tip structure is really beneficial, basically we plot the current as a function of the applied voltage for the tip-like configuration and for the flat device. And we see that the tip structure gives lower switching voltage and better cycle-to-cycle variance. In addition to that, we have binary switching, 1 and 0, which is non-volatile, with 50,000 cycles. And you can see that where we plot the resistance. In the on state is the red, and the off state is the blue. And we can have 50,000 cycles without any degradation. And most importantly, we send an applied voltage, the black one, and we get the response of the device, the red one, and we see that this device is switching with 7.5 nanoseconds, which is roughly an energy of 17.8 femtojoule, which is again, in the field of memristor is really a very good number. And this basically results here are very promising, and this is why we think this device could be a good candidate for low power neuromorphic applications. But the nice thing, it's not only the fact that we have a binary operation. Now, if we plot the resistance as a function of the number of pulses, we can gradually tune the resistance from the low resistance state to the high resistance states. And if we also send negative pulses, we can erase the resistance of the device again in an analog, quasi-analog way. So the programming voltage can form again intermediate states and thus continuously tune the resistance of the device. So as I show also in the introduction here, we prove that we don't have only binary storage, but also multi-bit storage in a single device. How do we use that to perform neuromorphic operation? And here I will show you 3 examples, basically. The first example is the hardware scalar multiplication. Here, what we have a device that is basically represented with a conductance G here. And when we apply a voltage, the current that will flow out is basically, it is equal to the conductance multiplied by the voltage. Now, we can, of course, choose the voltages, but of course, we can choose also the device conductances. This means that we can map the two inputs, to conductance and voltages, and what we get a result is just by reading the current. So we choose the voltages, we get the conductance, and how we read the result, how we get the result, we just read the current. So naturally, in this kind of devices, since they are resistors, the current will be the product of conductance and voltage. So the result, if we read basically the current, we get immediately the result of this multiplication. And what you can see here, it is an experimental output. So it is the measurement basically of the current, and here it's the software matrix multiplication result, again in milliamps. And what we can see that experiments are basically matched with the software, which is a good indication that what we are doing is correct. Again, here I would like to stress the point that if we control nicely the conductance here, we get much more accurate results, and this can be understood. If we send a specific voltage, we need to know which exactly conductance we get, and if we have, for example, stochasticity effect that plays a negative role, then we don't know exactly what conductances we get. So the multiplication is becoming more difficult. And the second, go one step basically further, we present also the vector matrix multiplication, which is really important when, for example, in deep neural networks. And what you can see here, here you can see the formula that we estimate the vector matrix, that we can perform vector matrix multiplication, where Y basically is the output vector, A is the matrix, and X is the input vector. Now, if we move to a crossbar, and each crossbar here, we have a memristor, and now if we apply voltage on these horizontal lines, we can estimate basically the current flowing as follows. For every conductance, the Ohm's law is applied, and we have basically a multiplication, and in every column here, the Kirchhoff's law is applied, and we have the summation or the accumulation. So now the total current that will pass through this line, let's say, will be given by this equation here. Okay, and as you can see, this equation, it matches exactly with the formula that is of the vector matrix multiplication, with the conductances G taking the role basically of the matrix A. So to do hardware vector multiplication, we do exactly what we did with the scalar case. So we map the input vectors to voltage, we map the matrix to conductance, and we read basically the result, and we read basically the result by reading basically the current. So what we can do multiply an accumulation experiment in a single step. We don't need basically to transfer information back and forth from the memory and the processing unit. We just need to read the current and we get the result. And this MAC operation is very important in neural networks and especially in image filtering. And this is our implementation of these 2x2 crossbar arrays, let's say. Here also I would like to give you an example of a hardware image convolution. I will not get on details, just I will provide you the message out of that. So if we perform this hardware image convolution with memristive crossbar arrays, the memristors that I just described you, we get 17 times more efficient than a specialized CMOS hardware, and this is because we don't have to shuttle information back and forth between the processing and the memory unit. So you can see this more details on this on this reference here. What we can do more, we can train basically a deep neural network for image classification. And for that, we have our partners that basically they built a 3-layer DNN network. It's a simple basically deep neural network, and was trained first on 60,000 100 digits, and then was tested on 10,000 new unseen images with and without light illumination. And what we provide to this deep neural network software is these experiments here, which is basically the conductance as a function of the number of pulses. So, and what we observe is that we managed to train an algorithm with 65% accuracy, which is not really basically good. And this was the case that we didn't illuminate our junction. But what we observe, and this is what we're going to publish soon, we observe that if we illuminate that junction, this memristor here, we can broaden basically the filament, and this is basically leading to more analog operation, and this analog operation improves the accuracy to 98%, which is very similar to the baseline, which is the perfect linear behavior. So my message here is that we managed to train NDNN for image classification using the aforementioned memristors. The input results into the software was the results presented here. It's the conductance as a function of the number of pulses. And what we see is that if the light is off, the accuracy is very low. If the light is on, because we get this linear operation, the accuracy is boosted to 98%. And this is quite nice because someone could basically envision actually an application where we use the light only when it's needed. For example, when a person tries to cross a road, which is an event that should be classified in very high accuracy, we use the light to enhance the accuracy only then. So when with that, we expect to save some energy out of that. So I think I will spend another 5 minutes to describe the 2 other applications and then or devices, let's say, and then I will conclude. The next device that I would like to describe is the atomic scale memristive photodetector. Why we need this? We need this because basically we need to convert the optical data into the electrical data and communicate that with a distant neurosynaptic array. So how it looks like? It looks like, as in the picture here, it consists of a silicon waveguide but coupled with a junction with a vertical tip. And the light is basically channels into the vertical tip and adiabatically focused at the level of the tip here. And the plasmonic hotspot that is formed at the level of the tip is what is basically modulating, reversibly pulls silver ions back and forth, and this is what is modulating an electrical signal. So what we have basically, we have an optical to electrical conversion using the relocation again of atoms. We don't have relocation of electrons, we have relocation of atoms. And this is key again, because as you will see later, out of this device, we can get memory, and the memory can be used for computation. So if we send an optical input, which has this waveform, we see that we get a resistance that is following the optical input waveform, and this means basically an optical signal is converted to a digital electronic response, and this is the results of this atomic electronic transport modification. I will not show the technology. Briefly, we know how to make basically gratings for coupling light in. We know how to make waveguides. This is the waveguides here. The cross section is shown here, and we know how to make basically memristors that are efficient interacting with light. And what you can see is the memristor is here. Here is the silicon waveguide, and here is the area where the light is interacting with memristors. So we perform several thousand of cycles, and we show that this is indeed a device that is working properly. We modulate back and forth these atomic configurations here, and it works. And moreover, we prove, but I will not get on details on that, that these devices work also on atomic scale. And this is because we see some conductance quantization when we plot the conductance histogram. Most importantly, and I would like to spend 1 or 2 minutes here, we see for the first time that we have a memory as a function of the optical power, as a function of the optical power, and not as a function of the voltage. Remember, whatever demonstration I show you until now, it was current as a function of the voltage. Now here we have optical power, and we have memory effect, and this memory effect, we take it in advantage, for example, to emulate in the optical domain the neuronal spiking behavior. Here you can see the conductance of the device as a function of the time when we send several optical pulses. And what we see is that after 4 pulses, the conductance state is reduced. After 11 pulses, it's again reduced. After 19 pulses, again reduced. And when we reach this threshold here, we have an abrupt change of the configuration of our memristor. And this is basically induce some abrupt changes on the state of the device, which is equal basically to the spiking behavior of a neuron. And the next step that we're working now is to get in advantage this behavior, to introduce it into a spiking neural networks to perform some, to show some application. Another thing that we would like to do, we didn't actually, we're working on that, is to move a little bit more towards bio-inspired computation. What we see is that recently neuroscience shows that learning depends not only on the pre and postsynaptic firing neurons, but also depends of an additional third factor, and this is a neuromodulator. And for example, the dopamine globally affect the functionality of synapse, and it is the origin, and it is at the origin of reward-driven learning. So, and we would like to make that also the same exactly in silicon. We integrate several electro-optical synapses within the silicon waveguide, and we show, we didn't publish it yet, that light can globally affect basically all the electro-optical synapses that you see here, which are basically memristors. And with that, we can really train a maze towards the cheese and not to the other direction. So basically, to sum up, we use the light as a third independent stimulus to enhance learning, and this is basically inspired by the neo-Hebbian learning originally invented by neuroscientists. So the last part that I will be really quick is it is an old demonstration that is back to 2016. It is the device that basically is converting the electrical signals here into the optical signals. And this device is basically the modulator, but in our case, it's not only a modulator, it's a memristive modulator, meaning that it has also some memory effect. And here you can see how the demonstration look like. And here you can see an SEM picture of the fabricated device. And here in the middle, you can see that there is a tiny nanofilament. The light is propagating in this black area here. And when we modulate this nanofilament here by voltage, we can modulate also the optical signal that is passing through this junction here. So modest voltage can reversibly basically pull silver ions back and forth, and this is what is modulating the optical signal. The important, again, thing that I would like to mention here is that if we plot now the current as a function of the voltage, this is the black one, we get the standard memory behavior of memristor. But if we measure also the optical transmittance through the memristors, we get also a memory characteristic. And this memory effect in the optical transmission could potentially use to mimic the integrate and fire functionality, similar to what we have in the photo detection experiment. For the moment, we don't have such a measurement. So to summarize this part 3, I show you that basically we're working on an electro-optical solution for efficient neuromorphic computing, but to have the whole integration, first we need to have the individual components. And we developed the electronic memristor, which is basically the basic component for this neurosynaptic core 1 and 2. We developed the memristive photodetector, which is able to convert the optical signal back to electrical signal. It is further equipped with the memory characteristic that it can give also some firing, let's say, functionalities, which is similar to neurons. And we also develop the memristive modulators, which are converting the electrical signal into the optical. Again, here we have the memory effect that can be used to make not only routing, but also computation. Of course, what is remaining now, and this is what we are working in our group, is to integrate all these functions together. So let me conclude. So I show you, I think, an electro-optical platform taking advantage of both the high density of electronics and the high bandwidth of photonics is showing a potential for low. We think that is the way to go towards low power neuromorphic computing. We think that the purely electrical one will not work. We'll face the problem of shuttling information between the different neurosynaptic arrays. Even if we perform in-memory computing, the scaling up will be a problem. And for that, we developed the key built-in blocks required for this electro-optical neuromorphic platform. And this is the memristive electronic switch, the memristive photodetector, and the memristive modulator. And we also developed the technology of integration of memristive components with plasmonic photonic circuits. This is really nice, and it is our basically it's the main strength of our group. And for the first time, we have atoms rather than electrons that are used to interact with photons or with electrical signal. And this is key if we would like to move towards more. Thank you for your attention, and I would like also to thank our funding sources, ETH Zurich, Siemens Foundation, and the Volkswagen Stiftung. Thank you for your attention, and I hope that I can answer your questions.
Thank you very much, Dr. Emboras. That was a fantastic talk. Yeah, as you said, please can we move on to questions. If anyone has any questions, you can unmute your microphone and go ahead and ask. Professor Alexandros?
Yeah, hi, Alexandros. Thanks very much for this impressive talk. So I am not familiar with the hardware, of course, but are there alternatives to neuromorphic computing to what you have shown us? What is the landscape there?
In the hardware level, you mean?
Yeah, in the hardware level.
Yes. So, I mean, one candidate for in the hardware level, of course, is the memristor, and in the field of memristor, there are basically 3 different technologies that are competing each other. We don't know which one will win at the end, but there are also groups in the industry, for example, that are working with charge-based devices. So, for example, the standard non-volatile charge-based devices, where they modifying the behavior of the device by incrementally changing the charge into a floating gate, basically. So these are the 2 basically technologies that I currently know that, and of course there is the CMOS technology, where they're using basically different components like capacitors and resistors to emulate some neuromorphic behaviors. So I will say there are these 3 technologies: is the CMOS, is the charge base, and the memristors.
Okay. And
the CMOS, the disadvantage of CMOS is that in order to emulate a single neuronal behavior, you need several components, and you need capacitors, which is extremely large compared to the memristors.
And out of curiosity, I mean, these machine learning applications, I mean, so you are doing this within your group, and I mean, how is this exactly done? I mean, you have a prototype system where you...
So what we have basically in our group, we have, not in my group, in our institute, let's say, we have people that are working on the development of neural networks. And what we provide to them is basically the experimental data given, for example, we provide them the conductance change as a function of the number of pulse. And those guys, which are more in the simulation part, they introduce that into their deep neural networks. So we are not developing basically these networks.
So you just give data to them, and then they apply this. This is how they. Mm-hmm.
Yes, basically yes.
Okay. Okay.
So
thank
they
you.
do. Yeah.
Vangelis, please go ahead.
Yes, thank you very much, Alexandros, for very interesting this presentation. I'm just wondering for a couple of questions. Actually, the first one is a little basic, so I don't know if it's relevant, but when you go to the single atom, let's say, I mean, materials and the methods, are the fluctuations there relevant in the formation of materials or?
Yeah, I think fluctuation and stochasticity there is at least for the applications that we are looking, is a little bit a problem, because stochasticity can induce basically a conductance value that could not be the one that we expect. And when we simulate that in deep neural networks, for example, we need to know exactly if we apply specific voltage, what is the amount of conductance that we get. So since we're working on this atomistic level, this fluctuation exists because this is the nature, and this could be a potential problem in the accuracy, for example, when we train an algorithm.
So is there any way to overcome this, or is more?
So one way that we use to overcome is we use this ultra sharp tip that I show here. And instead of creating several filaments, we at least create a single filament. So this reduces the stochasticity effect. Of course, at the end, the operation is happening on atomistic level. Still, we have some stochasticity, but the performance of the device were improved. Yeah, of course, it's not yet optimum, but one way is to basically localize the field and just avoid the formation of other nanofilaments.
Okay, thank you. And another one, if I may, which is related actually with the size of the problem. So it's not again clear to me, but does the overall, let's say, operation depends on the size of the problem? How does it scale up with let's say, when you increase the data set in the system? Is this an issue or not really?
I didn't understand this question.
I mean, when you presented some examples, right, with the matrix vector multiplication or with I'm just wondering whether the whole operation depends on the size of the data set, or the size of the problem, on the sum that you have there, for example, when you have very large matrices.
I'm not sure if there is, for example, for this hardware matrix vector multiplication, I think they show really, maybe here, they show here, for example, 128 by 64 crossbar arrays. Here, I don't see any problem, because you just, the multiplication here, of course, the stochasticity here, again, will induce some uncertainty into this conductance value here. Of course, the larger the data set, probably the more pronounced will be the problem. But at least we have, for example, and what I know, we have this kind of crossbar arrays that are working quite basically well.
So let me rephrase a little bit the question.
Yeah.
So if we, let's say, increase the size of the problem, do you see the same speed up that you observe compared to the standard, let's say, technology?
You mean if we increase the size of the problem, you mean if we increase the crossbar array here?
for this problem if you increase the size of the matrix? Of
yes,
the A?
Of the A, yeah, I see. So if we increase the size of A, which means that we increase the size of G, which means that we have basically larger crossbar arrays. So there, with respect to stochasticity, of course, since the size will be larger, the effect, I think, will be more dominant. But in what I can say is that in this small demonstration that we have here, 128 by 64, we already perform better than the standard CMOS processor, which was designed for making this hardware image convolution.
No, this is clear and it's really amazing. This. Okay, and just the last, maybe from curiosity. So how far away are we from, let's say, the industrial application of this in real systems?
Yeah, I think until now there is nothing available on the market based on memristors. The major problem that we need to solve is basically the repeatability and the reliability. I think there is a lot of research there. No one found the trick to make that device extremely reliable for industrial applications. Yeah, I mean, with this center here that I show you, we promised to Siemens that we're gonna solve this problem in 10 years. So we'll see.
It's a very difficult problem, again, related with stochastics.
Yeah, because it's an interplay of several parameters. So we have ion movements, we have oxidation reduction of atoms, and we have electronic transport. And this all should be combined in a way that it should be predictable. I think in each time that you apply pulse, there are, I think, 10 parameters that are changing. And these 10 parameters, you can imagine, should be really controllable. So, okay. But on the other hand, if we look on the brain, where the information is transported from one neuron to the other neuron through a synapse, and in this synapse we have the movement of atoms, it seems that the brain already found a solution how to reliably do that. So I'm probably looking deeper into this direction could provide us a solution.
Yeah, but is it, okay, now that it's a long discussion, but is it the same? I mean, here you are looking for something really deterministic. The mind, it might be stochastic and it's not a problem. But here you want, as you say, repeatability. Yeah.
Yeah, but this, I mean, of course, yeah, this is a big discussion, but what I would like to focus is in the, for example, in the brain, the atoms are moving through a liquid junction, right? So you don't have a solid state insulator there. You have just an insulator, which is a liquid, basically. You have a liquid electrolyte, and probably the barrier there, for example, is very, very low, and the way that the atoms are moving is less deterministic. So it could be one solution. I don't know the solution on this, but I mean, we're thinking to get inspiration from brain as well.
Okay, thank you. Thank you.
Are there any other questions? Okay, well, on that note, I would like to thank Dr. Amboras for your presentation today, for your time, and everyone for joining us in our last seminar of the semester. Have a lovely evening. Goodbye, everyone.
Have a lovely evening. Bye.
Bye. Thank you.